east coast of Africa. Our scientists face their toughest trial yet as they take on the ocean. They have to complete a set of marine challenges with a few simple tools, basic kit and a boatload of ingenuity. Our base on the Indian Ocean is a traditional fishing dhow, and our site on land is an isolated beachside workshop. It's destination paradise for rough science. Our 4 scientists are Kathy Sykes, a resourceful physicist with boundless energy. Mike Bullivant, an imaginative chemist who embraces the near impossible. Ellen Macaulay, a fearless have-a-go botanist from Missouri. Jonathan Hare, physicist, inspired inventor and artistic engineer. And me, Kate Humble, an experienced diver. I'm going underwater to put their inventions to the ultimate test. Together we are Rough Science. This week, our scientists will be set their most ambitious challenge so far, to protect a coral reef. We're snorkeling above the reef around Chumbe, a tiny island off Zanzibar. 400 species of tropical fish and 200 kinds of coral thrive here. But the survival of this unique reef is threatened by fishing boats and passing ships, and that's why we're here. Well, what did you think of that? Isn't it absolutely stunning?
Beautiful.
Oh, beautiful, beautiful coral, isn't it? This is a marine reserve, but at the moment, it's unprotected. There's no sign where the coral begins. So, that's where you lot come in. Mike and Jonathan, can you come up with some sort of device, some sort of warning system, if you like, for boats so that they know that they're coming close to the reef, but it keeps them far enough away that stray anchors or anything can't touch the coral? And Kathy and Ellen, there's a 300-metre exclusion zone here. So what you need to do is find a point roughly 300 metres from shore and then devise some sort of means of keeping Jonathan and Mike's device in that spot. You've got 3 days. Obviously everything at the workshop that you need, anything that you can find on the island, and of course, the magic trick. So the team have to protect this precious coral by building an alarm system that keeps the boats away. Ellen and Kathy are going to check out the spot where the alarm system will need to be anchored on day 3. It's on the edge of the exclusion zone just beyond the coral reef.
It looks pretty deep.
It does.
Now, we're going to have to measure the depth so that we can attach a big weight to the seafloor, have a rope going up to something.
Well, and then also we're going to have whatever they have as the system floating.
Yeah.
I think I can handle the floating bit.
Okay, so I'll find something to measure the depth and make sure it can cope with a tidal difference too.
Okay. And I'll handle the floats.
Great.
Their job is to secure a raft to the seabed with the right length of rope. If they get it wrong, strong currents could drag the alarm onto the coral and damage it. Back at the workshop, Jonathan and Mike are drawing up the design for an alarm system that will work out at sea.
One idea maybe is, if you imagine this is the water, if we have in the water a load of sort of buoys, like made out of a rod,
Right.
a piece of wood, and then we can have a wire that goes above the sea.
Tripwire.
Yeah.
So some alarm system that's triggered by a boat approaching the reef.
Yeah. And that sets the alarm off, which they can hear.
Yeah.
I think lights are no good, because in the day you're just not going to see it. It's so bright out there.
Yeah.
But a large bleep, you hear that hundreds of metres away. And so if a boat comes along, obviously the front of the boat is going to be wet because it's going through the water. It will make a circuit and trigger the alarm.
All right, so you're building an incomplete electric circuit, which is completed by a boat touching the wire.
Yeah.
Genius.
Mike goes beachcombing for materials, and Jonathan's got to work out how to power the alarm in seawater where there's no electricity supply. And he's had another bright idea.
We got one of these things given to us in the trunk. This is a little garden light.
Yeah.
And it's got solar cells on it. And so we can charge up in the day using the solar cells, the thing.
That'll work, won't it?
Yeah, absolutely, but it won't work at night.
Oh, no.
Or if it's cloudy, perhaps.
Oh, no.
So we need a 24-hour power solution. So the other way is to use wave power. then we got sun and wave. Then we can power it 24 hours a day.
That would be fantastic.
Yeah, and there's an incredible amount of energy in a wave. You know, it can pick up something like a QE2, a really heavy boat, and just lift it up and put it down again, just with one wave going past.
I mean, people have been trying to harness wave power for years, and no one's been terribly successful.
No, well, I think we just make a really simple little generator.
Right.
Something like this. I've just got a can here, a photographic can, and with wire on it, and a magnet. The key to making electricity is you need wire, you need magnets, and you need movement. You can either move the wire or you can move the magnet. So if I put the lid on here and shake it, you can see you make electricity. There's no battery there or anything.
Let me have a go. So clever. But Mike's fence posts are a bit more rough and ready.
Well, this is the prototype of one of the support posts. I've got to make sure that it floats more or less upright in the water. It will bob about like that. And it's weighted with a piece of old rock. And I just have to make sure that this one works and does its business. What I've just been doing is determining the optimum height for this bottle. If the bottle's too low down, too close to the weight, this thing will be very unstable. If it's too high, well, we don't have enough distance between the wire, the trip wire, and sea level. So that, I think, is about the optimum height for the bottle, and that's what I'll go with. This is my template. I'll make 20 of these. Quite an easy morning, really.
Ellen and Kathy have returned from the reef and they've got their work cut out for them. Ellen gets going on her raft. Kathy will have to measure the anchor rope for it. But getting the rope the right length doesn't seem to be straightforward.
Now, I need to measure the depth of water somehow, and the obvious way is just to take a weight, if you imagine that's a weight, and drop it down from the surface, and then measure the length of rope. And I might well do that anyway. But my worry is that the currents were really strong when we were snorkeling out there. And so I think that as this weight is being dropped down a distance that I think is quite big, it might get swept by the current a bit. So I end up, instead of having a nice kind of vertical rope measuring the depth, I might have the rope at a diagonal measuring something quite a bit bigger than the depth. So I'm thinking about trying to build something that might do a better job than that. And then this is it.
So Kathy thinks she can measure depth in strong ocean currents with a drain pipe and empty water bottles. Meanwhile, Jonathan's managed to scale up his generator for the alarm. So is this the wave power machine?
Yeah, this is going to be on Ellen's platform that's moving about in the sea. And we've got some magnets on the end of this ruler. So as it moves, the magnets wobble about, and you can see it's generating electricity.
Oh, yeah.
So if you wobble this,
all right,
that will generate electricity. And I can connect this up and you'll hear it works. No batteries or anything.
He's adapted a smoke detector to sound the alarm.
If there's any waves at all,
it works. The generator looks promising on the workbench, but will Ellen's raft be strong enough to carry it out at sea?
It looks like it supports its own weight. Now the question is, will it support the weight of anything else?
Might just need a bit more finessing. Kathy's been tinkering with her drain pipe so she can work out exactly the right length of rope to anchor the raft. She thinks she's found a way to measure that depth in powerful currents. Kathy, what on earth is this? It looks like you've been building a missile.
It is meant to be a depth gauge cake.
Right.
You see, this will fall to the seabed.
Yeah.
And when it does so, it will make a noise because there's a big heavy weight at the end on a big pole that goes up through here. Bang on the seabed. This is actually going to hit into that pole.
Oh, yeah.
So the thing crashes.
Yeah.
So I'm going to sit at the surface, drop it in.
Yeah.
And then measure the time it takes from it going in to hitting the seabed.
Right. And you'll hear the crash, will you?
I hope so.
Surely you're going to have the same problems with this as you would dropping a rock on a piece of rope.
Well, the thing is, even if this does get carried by the current a bit,
Yeah.
because it's falling just under the force of gravity, it can still be carried off to the side like that, but it will still take just as long to hit the bottom.
Oh, right.
Even
So
if it
it'll
moves in
be,
the
the
currents.
reading will be exactly the same whether it falls straight down or it
if
goes
it goes
slightly
off.
skew. Kathy's sure her tin tray depth gauge will take the same time to reach the seabed, even if currents drag it to the side. Mike's already assembled 20 fence posts for the alarm system, and he's keen to show off his master craftsmanship. What are you doing?
Back to the drawing board. This is the support system for the tripwire.
Oh, wow.
And the tripwire will just pass through. So these are
Brilliant.
just
So
supports.
these will stand vertically in the water.
More or less. They'll bob about.
Yeah.
But they'll hold the tripwire above the water.
Brilliant.
Because we're running it over 20 metres, you see, and it would just sag if we didn't have these 1.5 metres apart. We've got 20 metres of this. It will just sit in these cradles like that, supported. But I'll have to insulate it, otherwise
Okay.
we'd have an electric circuit, which we don't want. There's one slight concern I've got, and that is that in this environment with lots of seawater in the air, this will corrode. So I've got to think up some way of protecting it. There might be ways and means, but it does worry me.
It's the end of day one, and our scientists are all trying to make their own parts of the boat warning system work. Mike's so bothered about his tripwire rusting away, he does some overnight tests. Day 2. In just 24 hours, we have to build this unique alarm system out at sea. My first treat of the morning, Mike's got some rusty nails to show me.
I did a little experiment last night. I took a nail like that, and I just left it bobbing up and down in seawater, like our tripwire will be.
Yeah.
And look how it's rusted, just overnight.
That's amazing.
There's one way you can get over that, and that is to coat your metal with zinc. And that is a galvanised screw, and left for the same amount of time in seawater.
There's nothing on it at all.
No.
So are you proposing that you cover the entire length of the tripwire with zinc?
No, we don't have the resources to do that. There's a much simpler way of doing it. And in this third jar, what I've done with the nail this time is attach a strip of magnesium to either end. This nail hasn't corroded. It's been in the salt water for the same time, but you see, nothing's happened to it. No. What's happened is that the magnesium has corroded instead. It's sacrificed itself for the sake of the iron.
Are you saying now that you've got to find enough magnesium to run the whole length of that tripwire?
No, we don't need that much. All we need is about that much. Not many people know this, but a lot of pencil sharpeners are made of magnesium, so we just put that in the appropriate point in Jonathan's
Well, you just
circuit.
hang a pencil sharpener within the system, and that will do it?
It'll stop our tripwire corroding. It's strange but true. It's electrochemistry.
Saved by a pencil sharpener. But now it's Kathy's depth gauge that needs rescuing. She won't be able to cut the anchor rope to length unless she can hear the gauge hit the seabed.
What does work reasonably well, because I've been playing around with this in the sea, if you just have a big tube and you listen. But even so, you know, you can hear...
And what happens if you put a stethoscope on the tube?
Oh, that's an idea. The thing is, I think, because with stethoscopes, you're supposed to have them kind of pressed closely to something.
Yeah.
So I'd have to press it closely to a curved surface of a tube.
Yeah.
I mean,
Unless you put a balloon over the end of the tube.
And
No,
then
but
listen.
that sounds a bit mad, doesn't it? You could try it though.
Another fine idea, Dr. Hare. Ellen's had her own brainwave to make her raft more buoyant, so it'll carry Jonathan's generator. And the net is for what?
Basically, when I put this wood in the water yesterday, it was less dense than water, so it floated.
Okay.
But it's not buoyant enough to support much weight, so I don't think it would hold his generator.
Okay.
So what I thought we would do is stuff it with coconuts.
Why?
They've got a pretty good skin on them,
Yeah.
and the fibers trap air inside. These can float all the way across the ocean from one continent to another. So what I'm thinking is they can provide enough buoyancy
Right.
to support whatever Jonathan
So
makes.
these are going to effectively work like floats.
Yeah.
Hopefully there's enough air trapped in the outer layers of the coconuts to support my weight.
I am very happy. If it holds you, it'll hold anything Jonathan does.
Meanwhile, Mike's making some eye-catching additions to the fence.
I thought our tripwire would be more obvious if we had some flags attached to the poles. And this is turmeric. It's turmeric root. It's grown in Zanzibar. And you can see, if you cut the root, you get a beautiful yellow dye. And if we attach these pennants to our poles, then boats can't say they didn't see our tripwire.
And if Jonathan's generator works, boats should be able to hear the alarm system too. But if Kathy can't anchor it securely to the seabed, it could do more harm than good. She's now gone out in our dhow to test her depth gauge. To make it accurate, she needs to time it hitting the seabed in known depths of water. There are no currents at this spot, so first she drops a measuring rope straight down to find the exact depth. Now she's checking how long her gauge takes in this depth to hit the sea floor. Using the tube, a balloon and stethoscope, she listens out for the ping.
Okay, ready?
Yeah.
Set, go. That's great, thank you. So that was around 12 seconds, around about 12 metres.
To complete the test, she has to time it drop in 6 more places. She heads into deeper water. Meanwhile, Jonathan is finding out if his generator can be powered by the sun alone.
So I've got the covers on, so all this is to protect it from water. And I've also added the garden solar cells. So these are the little garden lights. So at the moment, because I'm not moving this, there's no wave power. It's being powered completely by the sun. So let's see if we get the bleep. We do. So if we just cover up the solar cell, then of course we don't have any energy from the sun, and we haven't got any energy at all, so the siren goes and we can't hear it. But if I give it some wave power now, we're getting it working. So now we have a completely environmentally friendly way of powering it. We've got the sun and we've got wave power.
Ellen's teamed up with Mike and they've found another use for the coconuts.
Yeah. Well, what do you think?
Well, I think having the coconuts as separators on the rope is better than not having anything.
For sure.
Because we don't want them to kind of collapse
All together
in.
like that.
Yeah.
And if the rafts at either end of the 20-metre tripwire are really well anchored,
Right.
it will give some tension to this.
Yeah, so between the two, I think we should be okay.
Yeah.
Are you happy?
Yeah, I'm happy. Let's go string some more coconuts.
All right.
Yeah.
Kathy's still bobbing about in open water, testing her depth gauge. It's painstaking work. Each reading takes half an hour.
You ready?
Yeah.
Okay, drop. Great, thank you. That was 15 seconds. 15 seconds at 15 metres.
Kathy needs 3 more readings to be certain of measuring the depth accurately tomorrow. At the end of the afternoon, Ellen's knee-deep in coconuts. And Jonathan and Mike have set up a dry run of the alarm.
The circuit's wired up.
Yeah.
It's being powered by the sun at the moment.
Yeah,
And there's 2 wires that come out of it.
yeah,
And the bleeper will only bleep if those 2 wires make a contact.
right,
One of them goes into the sea.
Yeah.
So wherever you go on the ocean, you'll get a conduction from that. The other wire goes up to our little tripwire,
yeah,
which is held by insulators on the posts.
right,
So at the moment, there's no connection between the 2 wires. But if our boat comes along now,
yeah,
imagine this is the hull of the boat, so it's
Yeah.
really wet because it's been going through the sea.
yeah,
and we make a connection between that wire and the sea.
Wow! So basically, the hull of the boat fills the gap in the connection.
Like flicking switch.
Sounds simple enough, but will a boat running into a 20-metre floating fence really make this alarm ring? Not long till we find out. It's day 3 and we're off to the island of Chumbe to install the alarm. The scientists are confident they've done everything they can to perfect their own part of the system. Now they need to join forces to make it work. When we get to the boundary of the exclusion zone, Kathy has to tell us the depth. Then we can cut the right length of anchor rope and secure the system exactly.
Let's measure the depth.
Okay, you know how long Ellen's ropes have got to be. Now what can I do?
When I say drop, drop.
Right.
And I'm going to listen out for the ping using my measuring tube.
What are you timing?
Now I'm going to time the time it takes for it to go from here to when it hits the bottom, which is when it goes ping. And from that, I'll be able to work out the depth from a test I did before.
Okay, fine.
Okay, is everybody ready? 3, 2, 1, drop. Okay, that's it.
How long was that?
27 seconds.
Now, so what does that tell you about the depth?
Well, I've drawn this beautiful graph, and it was incredibly linear.
So you drew this up yesterday?
That's it, and it's a much straighter line than I ever imagined. And it actually goes down at round about a metre a second.
Okay.
Approximately. If it's 27 seconds,
yeah,
that means it's around about 27 metres, plus or minus a couple of metres.
Okay, well, I'm going to try and get into a slightly more elegant position to tell you, to confess, that I snuck off when none of you were looking, and I came and dived this spot. And I lay on the bottom, looking at my dive computer, and the depth that it registered was 27.3 meters. Yes! So you're 0.3 out, Kathy says. Which means, Ellen, that you're going to need about 27 meters of rope for your boy. We're ready to build the fence with 140 coconuts, 20 fence posts, 60 meters of rope, a raft, and Jonathan's generator. It's time for me to take the plunge and help put all this together.
Nice to see you.
So we're going to put a flag at the end of a string of coconuts and then start to put the wires through the flags.
We have the buoy, string of coconuts, first flag, then another string of coconuts, then another flag, and then I'll start wiring up the wire between those two flags and carry on. We'll grow the fence. Okay, so here's the first flag. Okay, can I just see how it sits in the water? Fantastic.
Right, the flags are looking fantastic.
Good.
Mike and Ellen help me out in the water.
Another coconut!
Okay, some more coconuts.
Flag! Yep. Brilliant.
It's looking beautiful. Okay, the last one.
It's taken 2 hours to get this far, and we still have to thread the tripwire through the fence.
Pull, 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 okay, pull.
Just let Mike drift off. Okay, next one. A little bit more. More, please. Hold on, stop a minute.
But the wire's slipping off the fence posts.
That's come off the thing, that one. Can you wrap it round really tight? You need to do it with 2 hands. Couple of turns.
Stop! Grab the coconuts quick. Oh, God. Okay, we've had a coconut breakage. Let's wait. Can somebody pass me some rope, please?
As the fence grows, it's taking on a life of its own.
Stop pulling a minute. It's the stone on the rope.
Yep.
I don't want it to break.
Yep, that's 3.
Well done. Okay, the last one.
After 3 hours, we think it's sorted, but the sea is working against us.
The wire is really being pulled here.
I know.
With no anchor in place, the currents drag the fence out to sea.
Do you think you can swim round with that?
Okay, so we're swapping where Mike was.
Okay, go for it.
We've got this far, but now Jonathan's worried the tripwire isn't properly lined up.
What I wanted was all the little things, insulators that hold the wire, to be on one side. But I think they're zigzagging across. If that wire touches the wooden poles, it's going to set off the thing because they're wet. So I'm a little bit worried about that, but let's go for it anyway.
Finally, after 4 hours in the water, we've brought the fence up to the reef. The rafts are in the right spot. Time to throw down the anchors. My job's done. Ellen and I head back to the boat.
Well done, folks.
At the last minute, the final detail. Mike adds the magnesium pencil sharpener to prevent the tripwire corroding. Ready for a test then, Jonathan?
Well, yeah, we've got to stick this on Ellen's brilliant platform. This is the earthing's, well, the sea contact.
Yeah.
And I've got a clamp here. And now I just want to put it in here, make sure that it's secure. No, that's moving around lovely. OK, I'll turn it on. It should bleep just initially. OK, that's good. Now, if I make a contact, it should bleep. So if I put my hand in...
You're not going to electrocute yourself, are you?
My body's slightly conducting. And this is a very small signal. If I put my hand on there, it should go, eventually.
Oh, really? Fantastic.
So that works. So what we need to do now, Mike, put the crop clip onto the wire. Yeah, right on the wire there. Yeah, that's right. So that's not bleeping now, which means everything's working fine.
Yeah.
And if you like, the trip wire is sort of active now.
It's been a labour of love. After all this effort, it had better work.
OK, we're ready for the test with the boat.
Are you ready? Ready for the boat? I'll whistle.
Okay!
The Marine Park Rangers are standing by to run their boat into the fence.
Anyone have any idea? Do you think it's going to work?
Of course it's going to work.
Go off and never stop.
I think this is one of the most nervous moments I can remember.
And he's going so slowly.
It's coming closer.
We'll save the fish.
Oh.
Not quite on
the
it.
front of the boat
They need to
isn't
get
very
closer.
wet, though, is
They're
it?
not, no, they're not close enough. They haven't gone over it yet. They need to go over it. They're not quite on it.
That was absolutely extraordinary. That was the very first coral reef burglar alarm, and that was Rough Science. I hope you enjoyed it. Join us for more soon.
Next week, the team try and make me an underwater breathing apparatus so I can go swimming with the fishes. For a free magazine about all Open University programmes, call 0870 900 9581 or go to open2.net, where you'll also find more about this week's challenges.
Indian water clock, maybe in a temple.
Champagne, mingling, nice people.
In the shape of an enormous pie!
So there you have it. Comedy, business and history. An eclectic mix for a Wednesday night on BBC Two.
Over 100 years, one place